We are rolling. So, first, like I said, we're going to talk about some rules of integration that'll help you kind of get through some integral problems that might otherwise be accessible to you. The limits. So, if the upper limit and the small is the upper limit, I'd be like, well, we can't really do that, right? Because you need to start at the lower number and finish at the higher number. But this way, if you were so normally, if we do the integral from a to b, infinite rectangles, right? Getting more and more positive as we go. If it's b to a, we're switching through this way. So we're actually losing a little bit each time. That integral b to a, what you would have if you went a. Words. Calculate and switch it around. So the limits make sense, but then just make sure you throw a negative in front because it's going to have the opposite sign on it. Okay? First rule. The integral from a to a of f of x dx equals 0. Why is that one 0? You're not really going anywhere, right? Your lower limit and your upper limit are exactly the same thing. So have you really spread out any area at all then on your graph, whatever it is you have? No. So you'd have a height, but you would have no width to the area you're trying to calculate. So there's nothing there, no area actually there at all. So yeah. This is the whoops. The integral. You can take that constant and pull it out. Oh, I'll give you a quick example. Right? constant 0 to 1 x dx. That one. Same answer. Whether the 2 is in there or out. Does that make sense? Yes? Okay. So any function that you have, if you see, especially if you have some terms, which we'll get to in a little while, constant that you can factor out of it, you that out, bring it in front of the integral. Whatever you can do to simplify whatever is inside the integral, you're going to want to do that because it gets tricky down the road when we get to some functions that we can't visualize the graph, and some of the techniques we're going to learn about we can't use unless we simplify what's inside of there. So anytime you can pull out a number like that, that's going to be something. Multiple rule. These so basically, you're taking the integral of something that has multiple terms to it. Okay, something plus something plus something, something minus something plus something, whatever. Some kind of combination of things that are being added or subtracted together. And each one of those things you can think of as being like its own function. Okay? Together, we can break it apart. We can take it one chunk at a time if we're having things that are added or subtracted. Okay? Multiplying and dividing does not work that way, unfortunately. It'd be really nice if it does, but adding and subtracting will work for this. Okay. It's going to be one we use like constantly into separate integrals time and make it easier. Again, whatever you can do to make what's inside that integral something simpler, do it. So B of some function, and then you go B to C. F of x dx. Does that make sense? Basically, what you're doing there is you're taking this area that goes all the way from A to C, and you're chunking it, right? You're breaking it into two pieces. You find some number in between A and C, put it in the same, break it into two pieces. And so because doing the integral from a certain place to a certain place is easier than another. A little bit easier too. Then of the minimum value of the function you're looking at times b minus a is always dx. Larger integral. So, what the heck? I'll show you. And here somewhere. Okay, so here's the deal. The integral is the area under the curve from a to b. So this. Angle left. Yeah, right. You can kind of see the picture. It's a subset of the area of the integral. That rectangle. The minimum value. What's the length of that rectangle? So what's the area of that rectangle? Right, b minus a times the minimum. Oh, right there, right? So this is this minimum one, right? Definitely smaller than the integral. It's always going to be, right? Whatever the minimum, make that thing have to be lower. Rectangle. The max value. What's the width of that rectangle? B minus A. The area of that rectangle? This, right? The area of that rectangle definitely bigger than the integral, right? And it always will be. Okay? Could be equal to, if you happen to have a constant function. It would be the same. That's why I have the or equal to parts here. The f times b minus a will never be smaller than the integral, and then the b minus a will never be larger. Called the here, then if it's greater than g of x, it is higher on the graph, right? Its y values are up. So does it make sense then that its integral should be larger as well? Yeah. And then stuff exists. Way too. If f of x is less than equal to 0, then the integral, because the function is less than 0, the integral is less than 0. It's negative. Okay, it goes both ways, but typically we just do it this way. Just a little. One on your test. Anybody taking one there? But I know the answer. Out some on the that you can't do. There are some there's not enough information given to be able to do it. So if there's an answer you can get from the blank, in the blank. Good. All right, B. X. 3. Yep. It's this one plus this one, right? In here, so it's going to be, so 2 times -1 to 1 of f of x is 2 times 5 plus 3 times 3 times. Right. X. Can't do it. The limit is far out. We have no idea what that function is going to do in that extra space, right? So it doesn't necessarily double the size of the area just because the limits are twice as far out. Okay? So that's an NA. Can't do that. Can't do one either. Yep. One to 4. So do that. Add value. Means the following. Values, right? This thing point, the average y value was, how would you do that? How do you find the average of anything? Mm-hmm. That would give you the average of the 2 endpoints. I want the average of all the points. So when you find an average of a whole bunch of things, what do? Add them up and then divide by how many you have, right? So we would add the y values in here and then divide by how many of those we added up. The problem is this is a nice continuous, infinite number of points in between these 2 points kind of function. So finding the average value, average y value, infinite number of points, can't really do that. Okay. essentially and divide. Finds an area when that dimension is changing. Problem. We had. Yesterday. We can. What's the average value? So a good. Doesn't mean it's necessarily going to be that way, but that one up then. Over 2 then. Flip that. Let's go ahead and do that on the calculator. That in. So I'm hoping this integral comes out to 1, because it should. What is that exactly? 2 divided by pi? going to be somewhere close to a half. It's actually makes sense what we're doing there and how it works. Somewhere in the interval, take average value. Because minus a, the function at some point in the interval, the average value. Kind of like we talked before, that if you have some function that's continuous from a to b, it's going to have to hit every value between a and b. That was the mean value theorem we talked about before. And this is saying further somewhere on that interval. Some point to get from one endpoint to the other. If you look